Welcome back. We're going to talk now about derivatives of Michael additions. Pretty much, if you carry out the same reaction with an enone, but instead of using an enolate as a nucleophile, if you switch to other reagents, then you're looking at the derivatives of Michael additions. One of them is the use of lithium cuprates as the nucleophile. And what you end up doing here is simply um, placing that alkyl component of the cuprate salt onto the beta position of your enone. And since that yields an enolate that is activated at the alpha position, you can then do SN2 reactions if you choose, or you could react this with water to simply quench it. But yeah, you have the option of alkylating that alpha position if you want to. So the mechanism is very much reminiscent of what we did in the regular Michael addition. First, your nucleophile attacks your enone substrate at the beta position. The electrons of that pi system relocate to the carbon next door, and the carbonyl pi electrons move over to the oxygen to create a new enolate. That enolate can then be uh, subjected to an alkyl halide, a good SN2 substrate, um, which will allow the enolate to reform the carbonyl bond, and the pi electrons here will attack your carbon substrate, thus leaving or allowing the leaving group to take off. And now you have functionalized the alpha position as well as the beta position of what used to be an enone. Another reaction that kind of follows on those footsteps is the selectride reduction. Selectride is a very specific name that we give to a very bulky version of borohydride, um, specifically trisec-butyl borohydride. Depending on the metal, this could be lithium selectride, sodium selectride, potassium selectride. The one that I have here in the slides is sodium selectride. This is under low temperature, however. And the reason for this is that you may remember from OCHEM 1 that borohydride can serve as a reducting agent to the carbonyl directly. In essence, the hydride attacks the carbonyl carbon and turns this into an alcohol. To prevent that from happening and instead have the hydride attack the beta position of the enone, that's why we switched to a much bulkier version of borohydride to make it more difficult for the reagent to approach the carbonyl. And lowering the temperature to -78 kind of like cements the deal. It sets it in stone that yeah, the carbonyl carbon is not going to get attacked. Instead, the beta hydride or the beta position will be attacked by the hydride. So your mechanism is the typical thing we've seen before. Now I'm drawing out selectride completely, so you can see the 3-sec-butyl chains on the borohydride. The hydride attacks the beta position. This is all done at low temperature. The pi electrons move over to the adjacent carbon. The pi electrons of the carbonyl bond move over to the oxygen, generating your enolate. And that enolate can then be subjected to good SN2 substrates to pretty much reform the carbonyl double bond, have the pi set of electrons attack your methyl group, and of course the leaving group takes off at that point. Now in this case, since we have sodium here, we're going to expel sodium iodide as a byproduct, but we form the functionalized ketone in this process. Okay, so that's technically the idea. It's very similar to the cuprate, except that we're using a hydride instead of an alkyl to attack the beta position. Okay, and then the last derivative, which bears its own name, called the Stork enamine synthesis. This is named after Gilbert Stork, who pioneered this type of synthesis. We've talked a little bit about the type of chemistry that's going to go on here, so this may seem like a bit of a repeat, but then where it's going to differ is that we will introduce the use of enamines as nucleophiles for addition onto enones. So technically speaking, we have something like a ketone right here, so cyclohexanone, reacting with this enone highlighted here in blue. Now, by itself, this reaction really wouldn't go forward, but what that's the trick is to introduce a secondary amine with a little bit of acid catalyst to kind of get the process going. and you follow that up by acidifying the solution at the very end. This allows you to functionalize the alpha position of that ketone, attacking the beta position of the enone in the process. So let me show you how this whole thing takes place. The first thing is that you have to form the enamine. That's why you're using a secondary amine in this process. And to remind you of the synthesis, this starts by having the carbonyl oxygen getting protonated with the acid. The electrons go, in this case, back to oxygen in hydronium, and you generate your protonated carbonyl. That protonated carbonyl is now activated enough for your pyrrolidine, your secondary amine base, to attack the alpha, not the alpha, excuse me, the carbonyl position of that activated ketone. And so the electrons of that pi bond move over to oxygen, and now you have this ammonium hydroxy derivative, which itself reacts with an equivalent of water, the one that it may be around, or potentially an equivalent of your a second equivalent of your pyrrolidine, to remove the proton of your ammonium salt right here. The electrons go back to nitrogen, and then that hydronium that gets formed basically moves around and shuffles that proton, right? It basically dumps it onto the oxygen here. So the hydroxyl attacks the proton. Those electrons go back to oxygen to form water. And now you have a protonated alcohol, which serves as a very good leaving group. So your secondary, at this point tertiary, simply has its electrons come back down, kicking away the water leaving group and forming your iminium intermediate. That iminium intermediate is then tautomerized. Pretty much the alpha proton is removed, the electrons move over to the adjacent carbon, and the electrons of that pi bond move back to nitrogen to form your enamine. So that's pretty much a review of the chemistry we talked about with aldehydes and ketones. So this is kind of making a reappearance. So pretty much what Gilbert Stork took advantage of is that once you form this enamine, the alpha carbon becomes activated as a nucleophile. It's activated to attack electrophiles ultimately. So that's where the enone comes in, because once the enamine is formed, those electrons of nitrogen come back down, the pi set of electrons attack the beta position of your enone. The electrons of the alkene move over to the adjacent carbon, and the pi electrons of the carbonyl move to the oxygen to form an enolate. So we have the iminium enolate in the process. And then here's where you just quench the reaction. You introduce your water, and what that will do is it'll have the enolate, reform the carbonyl. The pi electrons take up the proton. Those electrons go back to oxygen, and you form your carbonyl. And further treatment with that aqueous acid will allow you to ultimately, if you pretty much follow the same mechanistic steps that I've gone through, form the enamine, but backwards, you remove the pyrrolidine base and you regenerate the carbonyl that you started the process with. So this is a pretty awesome way of making these functionalized ketones. In this case, it's technically a diketone, and the second ketone is not at the beta position. Technically speaking, this beta, not beta, but this ketone is not at the alpha, not at the beta, not at the gamma, but the delta position. So if wanted, you could introduce stronger bases like hydroxide, and then you can do like like Robinson annulation type reactions right here. So those are some things to keep in mind. But this will be a nice way of kind of doing that. Like just keep that in mind. Those delta dicarbonyls, can be enacted and synthesized using the Stork enamine synthesis. All right, and with that, we have finalized all the chemistry that we're going to talk about in this class pertaining to the alpha carbon of carbonyls. And yes, it was quite a topic, but hopefully, you're as happy as Gilbert was in this picture about learning all of this amazing material. Okay, so with that said, I'll catch you in the next lecture series. Bye-bye.